I want to do a short video on uh, week 5 project. And remember, we're doing these projects to really learn how to use StatDisk, the online version, and also pick up, kind of some information on the concepts. And this week, we're talking about this probability distribution called chi-square, and it's a very important continuous distribution, and it's used a lot for approximating discrete situations and continuous alike. So uh, we just have 3 examples of some different uses here, and and I want to go through and just show you how we're going to use StatDisk to come up with these, to do the computations and so on in hypothesis testing. So if we look here, we'll see, to complete this project, you just need to get into StatDisk and the online version. And the first part is the chi-square, what we call the goodness of fit test, equal frequencies. So goodness of fit is like what it sounds. It's how good does the data fit some predetermined percentages. Now we're working with a qualitative variable. And in this case, you can see this is day of the week. So if somebody responded on day of the week, what was the day where the um, visits occurred the most, we wouldn't say the answer was 20. We didn't ask that. Now you can see there's numbers here. That doesn't make it a quantitative variable. Those are just counts. Okay, for each of the variable is the day of the week. So if we asked a question about which day of the week most visits occur, the answer would be Monday, right? So again, the responses that we get are very important. Not how many responses we get of each one determine the type of variable that it is. Okay, so this is a qualitative variable, which we need for chi-square. And so to do this, uh, we start out when it says equal frequencies. That means that we're just going to assume that the emergency room visits are going to be the same. The number of emergency room visits are going to be the same every day of the week. Now, if you look at these numbers, we can see right away and say, well, they don't. But that's not enough. In statistics, we're really looking for um, models that are probabilistic in nature or have some probability. So when we think of it from a statistical standpoint, we're saying that roughly the number of visits that occur each day are the same. Okay, theoretically, we're testing are they exactly the same within reason, and if we fall too far away from those numbers being basically the same, then we have some probabilities that we use to build confidence and state that they don't. So our hypothesis test here is that the visits occur equally throughout the week. Okay, again, equal frequencies. And we're going to use the chi-square goodness of fit test. So we're going to move this over here and get into StatDisk. Okay, so we're in StatDisk, and we need to make that smaller. There we go. And it says here, test the claim that the frequencies are the same for every day of the week, level 1%. Well, we got to go into data sets. All right, data. Oh, there it is. Okay, I just had to scroll. When this is squeezed in like that, I can't see what I have down there. So there we go. So we need the editor, and we're not getting a bunch of data that's already been, up here. We don't want that. We want to type in this data that's given here. Okay. So you're going to type this data in. Now remember, I'm going to type in fictitious data. I'm not going to do your project for you. So what I do is I'm just going to make up numbers and I'll make up, that's 7 days of the week, right? So Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. Now for you, you would put in 20, 15, then 9, 8, 12, 15, and 6, right? So you put these days of the week in up and down, just like this. Mondays count, Tuesdays count, Wednesdays, Thursday, Friday. Okay, good. So we got every day. And then simply I'm going to go to analysis, goodness of fit, equal frequencies, right? And my significance level, I think it says 1%. So I'm going to put a 1. Column to be observed, meaning where's the data, right? The data is in column 1. Okay, so and evaluate. Okay, results. However, let me, whoops, there it is. Okay, here's my results. The number of categories, well, 7, that was the 7 days of the week. Degrees of freedom, in this case, we had, it's n minus 1, or the number of categories minus 1 for this table. So that means there's 7 minus 1, or 6 degrees of freedom. The expected frequency, meaning what would we have expected in every one of these days? Okay, now this is what we would have done, and again, just kind of ignore this for a minute. Let's go up here. We would have taken and had to add these all up, okay? Add these numbers all up and divide by 7, since there's 7 days of the week, and that would have given us a number that would have been exact same for every one of those, right? So in my example, I would have had to add these numbers up, which I'm going to do right now with my calculator. So you just have to give me a minute. And I'm going to take 34 plus 22 plus 33 plus 45 plus 53 plus 46 plus 54. Okay, so I add up those 7 numbers and I get 287 total divided by 7. Okay, and I get 41. So that's what this is over here. Now we can see where that 41 comes from. This 41 means that if theoretically every day was exactly the same, for mine, not here, not here. All right, you're going to do your own these days here. So if things were exactly the same, that means in my example, every day would have been 41, 41, 41, 41, 41, 41, 41. You're going to do the same thing, add these up and divide by 7, but you're not going to get 41. Your number is going to be a lot smaller than that. Right? Okay. Test statistic, that's the chi-square. This x raised to the second power, it's chi-square. Test statistic, 20.19. The critical value is 16. So see, my test statistic is greater than the critical value. But we use the p-value, right? Because it says right here, what's the p-value? Well, right there it is. For me, it's 0.00256. Okay. Now, is that less than the significance level? Remember, our significance level is 1%. This number is less than 1%. That means we will reject the null hypothesis that the emergency room visits occur equally every day of the week. And that's my data here. So So statistically, we have evidence to show or support that no, they don't occur the same every day of the week. Okay, so the alternative hypothesis would be that they do not, are not equal, right? At least one of those days is significantly different from the other ones. It could be one or two or three, or they could all be significantly different from the other. We're only testing that one idea. Either they're all equal or they're not all equal. Okay. All right, so let me take this out of here and let's go to the next one. And this is a chi-square goodness of fit test, unequal frequencies. Okay. Chi-square goodness fit. So it's really the same idea, except we're not saying that in this case, choices of ice cream are going to come out all equal. Up here, we said, oh, let's theorize that they're all going to occur exactly the same, right? Same number of visits every day. That was the equal frequencies. Now we're saying, well, what if we don't want to say that? Well, we don't have to, because we can say whatever percentage we want. So, for example, the American Ice Cream Standards Committee stated that 40% of Americans like vanilla ice cream the best, 25% like chocolate the best, 35% like something other than those two. Okay. So those are obviously not equal frequencies. So we can test that just the same as we did up here. We just got to make sure we get the expected values in now, because we have to do that. We can't let the computer do that. It's going to do that, or we're going to have to do that. So we have to add these up just like we did before. To get the expected frequency, we added these up, divided by 7, because it's 7 days a week. Now, for these three, okay, I got to add these three up and see how many people total. And again, I'm not going to do the whole problem for you. I'm just going to show you, get this going. So I'm going to take 165 plus 111 plus 224. That's 500. So I have a total of 500. Now, if 40% of those 500 people like vanilla, how many is that? Okay. So in other words, we're saying 40% times 500, 0.40 times 500. There we go. Is 200. So if things were perfect in our sample, this would have been, excuse me, this would have been 200. So that's the expected value. What would the number be if things would have worked out perfectly? So we put that right here, 200, right? And then 25% like chocolate the best. And, we got 111. So it's not perfect. 25% times 500 is 125. So, well, it said 111. It should have been 125, theoretically speaking, right? And then we do the same for the last one. This one is 35% of 500. And then you get those. Then we're going to put those into, excuse me, into StatDisk. So let's go to StatDisk and get rid of those. All right. So what I need is my table here. The observed are going to go in column 1. So 165, 111, 224. All right. And then these numbers here that we generated, which I'm going to make up again. So again, be careful. Don't follow what I'm doing right here. I'm just making this up. I'm going to say 122 and, oops, let me back up. 100 and 150 and 250. I'm going to make this 250. I wanted to make sure they came out to the right amount, 500. So once you get this table filled out with the numbers in here, observed, expected, chi-square, goodness of fit, unequal expected frequencies. We can test this at 5%, it says. So we're going to leave this as 5% as counts. Okay, these are counts. Observed column. The observed values we put right here. Expected values we put right here in column 2. Evaluate. There we go. So we got 3 categories of ice cream, vanilla, chocolate, and others. So that's what that is. How'd they get the degrees of freedom of 2? Well, we got 3 of these, and then 3 minus 1 gave us 2. Okay, that's where they got the 2 from. And then test statistic, again, that's that number. When you use the formula, you can use a formula for chi-square test statistic, and you do the computations. That's the number you get. The computer does it for us. The critical value is a theoretical continuous distribution table that you can look up values or whatever, but the computer gives us that for us. So, and we get the p-value of 0. So again, this is my data. This is I made that up data, right? So be careful on yours. And it says, paste your results. The null and alternative hypothesis we talked about is that the observed and expected values would be the same for all 3 flavors of ice cream. What's your conclusions? Well, you look at the p-value, you look at your significance level, and then you conclude, right? P-value less than a significance level, reject the null hypothesis. Okay, so one more. Let's go into this chi-square. It's called the test of independence. And you'll notice now we have a ice cream flavor column, but now we have a gender column. Ice cream flavor is qualitative. Gender is qualitative. So we are comparing 2 qualitative variables. It's almost like correlation. It's not correlation. Correlation requires quantitative variables. Okay, these are not quantitative. You cannot do a correlation on qualitative variables, okay? But it's a very similar idea. What we're trying to do is do a test of independence, meaning not that one correlates to the other, but is one variable independently, affected by the other variable, meaning that men and women choose to like vanilla, chocolate, or other equally the same, okay, as their favorite ice cream. So what we're saying is that gender does not influence the type of ice cream that someone will say is their favorite, okay? So gender doesn't influence the percentage of people, men and women, that will say vanilla, right? Or the number of men or women that will say chocolate or something. All right, so again, what you're going to have to do is basically the same idea. But let's go over to, we're going to run a hypothesis test of independence. And let me move this over again. Okay. Web. So you're given the data. You don't have to figure anything out because there are no expected values given here. They will be calculated separately by the software, okay, the computer. So let's see. Significance level is 5%. Here we go. That's good. Counts. These are counts. That means there's 100 men that said vanilla was their favorite. This 120 means that there were 120 men in the survey that said chocolate was their favorite, and so on. The observed column. Okay, well, we're changing this. We're going to contingency table. Okay, this is a chi-square contingency table. When you're comparing rows and columns, okay, so it's a little more involved than what we did before. All right, so let's see. We've got to type in, and let's get to toggle sample edit. Okay, we've got to type this into here. Okay, just the way it is. And all right, let's go back. And so 100, 350, 120, and 200, 60. I'm just doing a little bit more this time for you. I want you to make sure you get that in the right way. So you type it in not in terms of rows and columns up in this way. You type it in how your table looks. Test of independence, because you can have as many rows and columns as you want. And so they want it to look just like that, just like the table. So, all right, so the vanilla, all right, 100, 350, the chocolate, and that. So that's it. And then we just basically evaluate. And sample must have at least 2 equal length columns containing at least 2 values. Whoops. Oh, okay. My fault. Got to go up here and select them. 1, 2, and 3. Okay. So good thing I did that, so you got an error and wouldn't have known. Now, so there's the data in columns 1, 2, and 3. Now what I'm going to do though is I am going to change the data. So don't worry, that's your data. I'm making this up because I don't want to give you the answer. All right. I don't want to give you the answer. So now let's go up here, columns 1, 2, and 3, and evaluate. And there we go. There's your chi-square test statistic, chi-square critical value. There's your p-value, and basically you do the same. How do we get 2 degrees of freedom? Again, basically with a contingency table, it's supposed to be row -1 times column -1. You don't have to really worry that much about it. We didn't get into a lot of talk of degrees of freedom in this course, but basically they're saying that if you take this table is a 2 by 3, and if I subtract 1 off the row and 1 off the columns, I end up with 2 degrees of freedom, or cells that could vary. Once these are determined, this row and this row, then these can vary. But so 3 minus 1 times 2 minus 1 is 2. That's where they get that. And then you got to answer these questions. Okay. So that's it for the Project 5 video.